All right, hello everyone. I'm going to start by actually showing you a couple of pictures here because when I first started teaching this, I assumed everybody knew what a washer was, but it turned out everybody did not. So before I actually show you what we're going to be doing in class in terms of a washer method, I wanted you to see what a washer is. It's kind of like a flat donut. It's a tool that you would use, all right, when we're screwing something in, whatever. So hopefully, if you didn't understand it, there you go. Hopefully for most of us, we already knew what that was, but just in case, I wanted to make sure that we knew what these were because I don't assume everybody does anymore. So that's a washer. The notes for the day is called the washer method, and it is still dealing with this idea at the top, volumes of a solid of revolution. So yesterday, or today, I guess, today's Friday for me, but whenever you're going to watch this, the last set of notes we did the disk method, there was not a hole in our solid when we revolved it. So that's what this is saying. So we're going to use a disk most likely. And when we rotate, that solid of a revolution did not have a hole in it. And the reason it wouldn't have a hole is because it borders the axis of revolution. So every problem we did, if you went back and looked at those notes, we were rotating it around a line that we bordered. So it was solid the entire way. A washer, there is going to be a hole. And that is because the solid of revolution does not border the axis of revolution. Okay, so that's why we're going to be able to have to be able to do something different than just the disk method, which is a solid circle. So the first couple here, all I'm going to have you do is sketch these in so we can see what this means. Then we'll actually do some of these below and on the back page. So what I want you to do, draw the figure formed by revolving the region enclosed by y equals root x. So there's our y equals root x. Y equals 1 like we did yesterday. So here's 1, and it's going to come right through here. And then x equals 4. So this is actually the same exact problem that we did yesterday in our notes. At least the setup is the same. That's our area. If you went back and looked at that problem, though, in that set of problems, I had you rotate that around the line y equals 1. Now what I'm asking you to rotate that around is the x-axis. So if we now take this region here, this blue region, and rotate that around the x-axis, and notice how there's a 1 unit gap from the line to the x-axis. So when we rotate this, it should create a reflection when we're thinking in 2 dimensions. So that would mean there'd be a 1 unit gap below where the line got rotated. And then the root x curve would look like this as it got rotated. So that in 2 dimensions, it would look like that. But in 3 dimensions, keep in mind the way we talked about those disks when we did those, we had all these rectangles that we started all this area stuff off with. So think about what would happen if each one of those rectangles gets rotated. The top of this rectangle, which is that radical curve, would get rotated around the front to the bottom, and then the back, and then right back to where we started from, creating a big circle. So that radical curve, as it gets rotated, creates that big circle. While the bottom of the radius, which is the horizontal line y equals 1, that's also getting rotated. And while that rotates around, that's creating this inner smaller circle. I showed you the picture of the washer because what happens is this is a solid all the way around. It's filling itself in around the front and then the bottom and then the side. And what we then end up with is a hole in the middle. And all of these would do the same thing. The radical creates the big circle on this one. It creates a smaller circle here. And then this is solid. And then the last one that I have drawn in, same thing, big circle. And then the inner smaller circle created by that line. And then we have our washer. So it still looks kind of like a bullet that we were talking about the other day when we did them. But what we would hopefully notice is that that bullet has a hole that's kind of bored out of it. So if we could drill a hole right through the middle of this, there's a hole in this. So if you could take your pencil, kind of slide it along your computer right now, it would slide right into there and you wouldn't be able to see your pencil. It would be hidden by that rotation. All right, you could kind of grab it, look down. It's almost like a microscope or a periscope where you would just look right down that long hole down the middle of it. That's our washers. So obviously we have a big hole in the middle, so it's no longer just going to be one circle. It's not going to be able to be a disc. All right, so number 2, same thing. I just want you to draw this. So we're going to do y equals x, which looks like this. Y equals x squared. So we don't necessarily need this over here. We don't need this. Where they're going to intersect is here. So this is y equals x squared. So our region now is this here. I want you to rotate that around the x-axis. So if I rotate that around the x-axis, it's going to look like this. So notice we're not rotating it around something that will allow this to be a completely solid shape. Take one of your rectangles in here that we would have used to find the area and rotate that around the x-axis as well. And you'll find the line that's on top becomes the line on the bottom, creating the big outer circle. The parabola, as it gets rotated, creates the inner smaller circle. And then as it fills itself in around it, we create our washer. Okay? So that's the difference between the disc and the washer. Discs, there are no holes. Washer, we're going to have a hole. So as you kind of read through all of this, you can kind of read through it all. What I want you to do ultimately for number 1 is find the volume of number 2 above. So let's go up to this problem. Actually, you know what? I'm going to have you do number 1 above just because I can actually draw this a little bit better and see what's going to go on. So we're going to find the volume of number 1 above. So let's change our directions to that. And then I'm going to do the work up here where we can see the graph. So hopefully what you're now seeing is we have 2 circles. So instead of just the 1 circle like you would have done in the disc method, we now have 2 circles. So if we want to figure out what the washer is, what we would really want to do is to figure out what is the area of the big circle. So I'm going to use R to denote the bigger radius of the bigger circle. If I were to find that, what that would give us is, try one more time in this, hopefully you'll see this big circle. Now, if we just did that, that would imply that everything inside of here is filled in. It's a solid, continuous disc in this case. Well, it's not. What we want to do is get rid of that hole that's in the middle. So we're then going to subtract away the area of the little circle. So that's why we'll use the lowercase r to indicate the smaller circle. So it's really the bigger circle minus the smaller circle. That difference is the washer. So if I now talk about what's the difference in those, that's going to be our washer. Well, it's not simply an area. Each one of these has a width to them. We don't want to find the volume of just one washer. We want to find the volume of not just these 3 washers. We want to find the volume of all of them. So that's what the integral is going to do for us. So that's basically the washer method. It's 2 circles, and we just want to find the difference in them. We're going to clean this up a little bit. Notice how they each have a common factor of pi. So we're going to pull that out. So the washer method will look like pi, and then still going from A to B. And then what we're going to want is the big radius squared. And so when we go to do these, we're going to have to define the big radius. We're going to subtract away the little radius squared. And then since these all have this W, that's our change in X. Since it's vertical, I'm going to factor that out, but I'm going to put it on the back end where it belongs. That's pretty much our washer method. So for this problem, if I want the big radius, so let's look at this big circle that I have right here. The big circle's radius would start at the top and go down to right in the middle. So if I ask you to define this radius here, wouldn't that be bordered on top by the radical, so root x, and then on bottom by the x-axis of 0? So that would define every big radius for every circle. If I go to this one, same thing. Big radius would have gone from root x down to the x-axis. Our little radius, I'll use this little circle. Hopefully you can see this. That little circle's radius would have gone from right here to here. So the little radius would be bordered on top by the line y equals 1, also bordered on the bottom by 0. So our little radius would be 1 minus a 0. Limits, if we are in terms of x, our limits have to be defined as x values. Definitely we finish over here at 4. And then just like we would have done the day before, the previous notes, we need to figure out where did those intersect. When we did that, we found that root x and y equals 1 equals each other at the x value of 1. So that ends up being our lower limit. That's our washer method. You could throw this into your calculator right now if you wanted. It's again, where do you want to spend your time? It's up to you. You could square that x real quick. It's really just x minus a 1. That's pretty easy to plug in if you just squared both of those. But then throw that into the calculator. All right, that's going to end up being our answer. So that's the washer method, just really two circles, biggest one minus the smallest one should leave you everything that's in between. All right, so let's crank a few of these out. If you go to number 2, it says find the volume of the solid formed by the region bounded by the curves x squared plus 1 and then y equals a negative x plus 3. We're going to rotate it around the x-axis. So this curve is a parabola that opens upwards, a vertex at 0, 1, and then this is a line with a y-intercept of 3 and a slope of negative 1. All right, so that's our space. I want you to rotate this around the x-axis. So take that space. Again, if there's a 1 unit gap from that vertex, there should be a 1 unit gap to the reflected vertex. So it should look kind of like this. That's our reflection. We have these rectangles in here that are getting rotated, so let's draw one of them in. Rotate that rectangle around the x-axis, and what happens is the top, which is really just the line, creates this big circle. The bottom of the radius here creates the inner smaller circle, and we end up forming our washer in here. Because it's the washer, our volume is going to be the sum from A to B of our big radius squared minus our small radius squared. And then the difference in x is our width. If we look at my washer, your washer, go to the big circle. Here's the top of the big circle. If I'm going to draw that radius in, it would extend down to 0. So the big radius is bordered on top by the line, negative x plus 3, and on the bottom by the x-axis, which is 0. If I want the little radius, then I go to the inner circle, the smaller circle in here, and its radius would be bordered on top by the parabola and on bottom by the x-axis. So here's my smaller circle. I didn't draw that particularly well. That's the top, that's the bottom. So the top of the small circle is the parabola. The bottom would be 0. Then we need our limits. So we would want to know where's the first washer. The first washer would have been drawn way over here where this area had started. So we want this intersection point, and the last one would have been here, that intersection point. So you set those two equations equal to each other, figure out where they intersect. So x squared plus a 1 equals a negative x plus a 3, x squared plus x minus a 2. All right, so what we find is they intersect at negative 2, so that's our lower limit, and a positive 1, that is your upper limit. That's that. Number 3, y equals x squared, y equals 4x. So yeah, here is x squared, and then 4x looks like this. So we don't really need the left-hand side of that parabola. Let's just deal with this guy. You're now rotating this around y equals a negative 2. So keep horizontal vertical lines straight. This is the y value of negative 2. We have a horizontal line here that we're going to rotate that blue region around. So this 2 unit gap should exist in the reflection. Boy, if I can draw this in. So that's our reflection. And then it's filling in itself as it gets rotated. So the line creates our big circle. And then the parabola, as it gets rotated, creates that inner smaller circle. The washer, so once again, pi, big radius squared, minus little radius squared, and then our width, since it's vertical, is our change in x. The big radius, if we come over here, My big radius is the top of the big circle, so that's right here. I'm going to extend the radius down to the middle, which should be right here. So notice what that's now bordering on the top and the bottom. The top of the big circle, the top of the big radius is the line 4x minus, and then the bottom of that radius, where we're right in the middle of the circle, is this line y equals a negative 2. So we do 4x minus a negative 2. That would define our big radius. Then we want our small radius. Let me get rid of this, hopefully. There we go. That worked pretty good. The small radius would be bordered on so the small radius, we look to the top of the small circle, and it's going to be bordered on top by the parabola, and it's bordered on the bottom by that same line y equals 2. So we now do the parabola x squared minus the negative 2. That's our small radius, and then these obviously are all added together, 4x plus 2, x squared plus 2. Those are our two radii. And then our limits, this definitely starts at 0, and then we would want to figure out where they intersect up here. So you just take your x squared, set it equal to 4x, solve that little equation. We get the 0 that we knew just by understanding the graph, and then we see that they would have intersected up at 4, so that ends up being our upper limit. All right. Before we do 4, let me just give you a little prep here. We want to make sure that you draw this somewhat close to number 5. So I guess you could just watch and just draw it where I'm going to draw it. Find the volume of the solid that results in the region bounded by x squared, and 8 minus x squared is rotated around the line y equals 8. So we're going to, if we draw this in, we want to draw our xy plane close to number 5. Actually, hold on, don't do that just yet. Make the x-axis right there. And then we have the parabola x squared. So here, the parabola 8 minus x squared. So our vertex is here at 8, and this parabola would now open downwards. And then when they intersect, that region is the region that we're working with. So we have the parabola y equals x squared, and then the parabola 8 minus x squared are those two curves. Maybe I don't want to draw that there. Just keep that in mind. I'm not going to write that yet. We're going to rotate it around the line y equals 8. So this is a horizontal line, and it just so happens to go through 8, which is the vertex of that second parabola. So this is our line y equals 8. So for the first time, this can happen with discs also. Instead of always rotating it downwards, we're going to flip it upwards. So we're going to rotate this around this line y equals 8. So now the reflection in 2 dimensions is up here. So that looks like this. When we rotate that, this curve here, bottom curve becomes the top curve, creating our big circle. And then right in here, we just get a really tiny little circle right in that middle. We see we have a washer, so we can jump right to this. Big radius squared minus your little radius squared. And then dx. If we were in class, I would have you try this one on your own, especially there's something we want to be careful of. So if you wanted to pause it and try it, you could try that. I'm going to go ahead. If I'm now going to define the big radius, what we want to be careful of, and this is normally why I have you try this one and give you a few minutes to think this through. If we go to draw our radius in like we have been from the top down to the middle, if I ask you what the top of this radius is right now, so the radius that I just drew in right here, if I ask you what the top curve is, so what's the equation for that curve, don't tell me that that's the 8 minus x squared, because 8 minus x squared should have a vertex at 8, not way up here. So this curve we don't necessarily know. You might be able to figure it out, and this one isn't too terrible to figure out. We could probably you could actually figure this out. But we don't really want to define the reflected curve. We always want to reference the original curve. So since we don't know what this function is, and we don't necessarily know what this other function is, because they're just the reflections of these two, what we always want to do is resort to defining all of our stuff with the original function. So there's nothing saying that I have to draw in my radius up here from the top to the middle, because I could do the bottom to the middle. And then by doing the bottom to the middle now, we still get the radius of the circle. It's just the bottom half for the radius. Now we do have a clear top and a bottom. But where this is now a little bit different, if I look at this radius that I just drew in right here, notice how now the top curve is this horizontal line 8, what we're rotating it around, so that has to go in first. And then the bottom of my radius, the bottom of that big circle, is x squared. When I go to do the small circle, really small circle, I don't know if I can really draw this in particularly well with this pen. I'm trying to make it a little smaller. So if we now go to that small circle, the radius would just be right in here. And we want to, again, draw it to the bottom where the area is actually defined. The top is the line 8 again. And now the bottom is this parabola right here. And that was the parabola 8 minus x squared. And since it's now binomial, we probably want to use parentheses here to make sure that negative gets distributed. So those are our big radius, little radius, and then we now need their intersection points to get our limits. So take your x squared, set it equal to 8 minus x squared, and then solve that. And then you have your limits as well. Plugging that in, just be careful, there's a lot of squareds there. Like I said before, it's not unusual for people to mess up the squareds. It's probably the most common mistake I see when people plug those things in. All right, number 5. What we got? Y equals x minus a 1. So I don't think you have to worry about where you draw this one. So we have a negative 1. So y equals x minus 1, and then 1 minus x squared. So vertex at 1, parabola opens downwards. Extend this. You're going to rotate that around the line y equals a negative 3. That just so happens to be this intersection point right here. So we're going to rotate this around that line. And now I look, it's going to be bad. Hopefully you didn't draw yours quite as big. But that should now extend down to here. Washers come in here. And then we set it up. So volume is pi big radius squared minus our little radius squared times our dx. So big radius would have extended from this parabola on down to what we're rotating around, that negative 3. So the parabola was 1 minus x squared minus a negative 3. And then our little radius would be right in here. The line is on top, and then the negative 3 is on the bottom. So x minus a 1 minus a negative 3. That's our little radius. The limits are the intersection points. So x minus 1 equals 1 minus x squared. And then we get 2 minus 1. So we should get limits of negative 2 and positive 1. All right, 6. Just going to make sure we're recording so I don't get lost and upset here. Yep, good. All right, so 6. A couple more. 4 minus x squared sine of x. So here's 4 minus x squared, and then the sine of x curve looks like this. So this is our region. Y equals a -2 down here. That's what we're rotating it around. So we're going to do this reflection. And then this is the reflected area. Big circles, little circles. And again, you can pause me, I'm guessing at this point. We're feeling pretty good about this. This is the last one vertical, and then we'll do 1 or 2 horizontals here in a second. So when we go to set this up, you have your pi. If we want the big radius, that's going to go from the parabola down to -2. Minus, and then we go to the little circle here. That's the sine curve bordering the little circle. On top, the -2 is still the bottom, so that's our little radius. And then our width is dx. Similar to what we did, we didn't do one of these with the cross sections, but on the quiz with area, we had to do this. When we now go to look for these intersection points, this is not something you're going to be able to do by hand when you set those equal to each other. So you can have to go to your calculator and do it that way. So let me try to open this up. You can do it. You'll probably do it just as fast as I will, faster by the time my calculator opens, and you can just check and see if we get the same answer, or fast forward until I actually get through it all. But graph those, find their intersections. You're going to want to store those as your A and your B so we don't lose any values in those. And then that's going to be your lower limit and then your upper limit. I'm afraid to pause right now, otherwise I would pause this, but I don't trust this. So we're going to wait. You can fast forward me if you like. There we go. All right, so we got sine of x, 1 minus x squared. And we want their intersections. So second calc, number 5. Intersections of -1.409624. I would store that. I'm going to write it here, but just know that 1.40964, that decimal continues on, so you're going to want to store it before you plug it in. And then second intersection point is 0.63673727. If I can remember all that, it's 0.6367367 maybe. That's what we then plug in. First 6 are all verticals, and then we'll just do one of these. I think you'll understand this, and then I'll put you out of your misery. Horizontal washers. So if we now, same thing we did with the discs, same thing we did with area, same thing we did with our cross sections. Look at how these are written. You're going to have to graph that most likely on your calculator, unless you know what these look like. So if I were to do that, I'm going to have x equals y squared. So that's a parabola that looks like this. And then x equals y cubed comes around like this, touch each other at 0, and then it's increased a little bit quickly, but then it kind of flattens out right in there. So it's actually a really tiny little area. So this is our area here. I'm going to then make this bigger just for the sake of what we're doing. So here's our parabola. And then the cube graph does this. Okay. There we go. That's better. There's a lot of stuff we don't need right there. So that's our graph. Let's label these because it's not easy to keep track of. This guy is the cubed, and then the one that's on top over here is our y squared. You're now going to rotate this around the y-axis. So if this now rotates around the y-axis, should look kind of like this. Like we talked about with our discs, if we're going to rotate that space around a vertical line, you can kind of think of the y-axis as a fence post, and then you start swinging the gate around the fence post, the types of circles that we're now creating through that rotation would have to be horizontal. So they're going to have to look like this. This is the rotation that we're using as we spin these around. That's why it's called horizontal washers in terms of this section. As soon as we go horizontal, hopefully now we're understanding, as soon as we go horizontal, everything has to be in terms of y. So this is still definitely a washer. We can see there the washer that I drew in. So you're still going to do pi. You're still going to do your radius, big radius squared. You're still going to do your little radius squared. But now the width, since they're horizontal, would be measured against the y-axis. So the big radius, here's the original space over here I have shaded in blue. The big radius would start over here at the big circle, go to what we're rotating around, which is the y-axis. So the big radius is now horizontal, so we want to be doing right minus left. The right curve is this one, which is the x squared graph. And then the y-axis is 0. If we go to define the little radius, that would just be right in here. And the right side is now the other curve, x equals y cubed, and then 0 to the left. So y cubed minus a 0. And then our limits, we probably should have figured these out just to make sure, but these do intersect at 1. So we're going from 0 to 1. And actually, I am going to do number 8 because if you want to turn me off, you could. And if you want to watch it, you can watch it. So let's go ahead and do number 8. So number 8 is just asking you to repeat number 7. So draw in kind of that same initial curve. So here's y squared. Here is y cubed. The only difference with this one is I'm asking you to rotate this around x equals a -2. So instead of the y-axis, we're going to go around this vertical line over here through x's, the x value of a -2. When we do that, it's going to kind of look like this. It's pretty bad, but hopefully you can draw that a little better than I can. That rotation around a y-axis is creating horizontal circles. So we'll draw that in. And there's our washer. So we go to set that up. My guess is you could probably do this on your own at this point, so go ahead. Big radius, see if you got this, would have started over here at the right side of the big circle to now -2. So now we would have the y squared curve minus the -2, so +2. When we define the little radius, that would have been right in here. So the radius of the little circle, the right-hand side is this curve right here, which is the y cubed curve. And then the left-hand side is the line -2. So y cubed +2. And then our limits would not have changed. We still start here, still going to this intersection point. We're still going 0 to 1. Quick reminder before you take off, you can do most of that assignment that's online. I think it's going to be due ultimately Tuesday night because we have one more set of notes that goes with this topic. So I'll do those on Monday. It'll then be due on Tuesday, but you can get most of it done. Only the couple problems that would pertain to Monday's notes you wouldn't be able to do. So if you want to get a head start on that, you could. All right, I think that's it. If you have any questions, feel free to ask on Monday. Come see me during Intervention Tuesday. Whatever questions you have, just let me know. All right, we'll see you guys later.